Hello and welcome. Thanks for coming that late on a Wednesday. I'm in a way competing with Elton John, right? Don't get to say that every day. So thanks for coming to the session. I'm pretty sure you will like this. This is typically a very popular topic. I'm talking about Java performance today, and I'll try to do it on a very basic level without looking at machine code or without looking at bytecode. And not because I don't think that you wouldn't get it, but the simple thing is that you have to spend some time to get used to these concepts, and actually they're not important if we talk about performance. What I'm trying to do today here is that I'll look through some concepts that are important, that are very crucial for the HotSpot Java virtual machine when the Java virtual machine runs your programs. And hopefully you will learn how you can apply some rules to your daily working to help the JVM to optimize your code, because ideally the Java virtual machine would be this magical box where you can put in any source code or bytecode rather, and then out comes super performant code, super performant machine code, and no matter what you do, it will run very fast. And that's unfortunately not true because it's impossible to implement, right? So it often helps to write code in a certain way to help the JVM to let you help you, right? I have a disclaimer slide here that everything I say today might not be true in the future, at least, right? So of course I do my best, you can always be wrong, but what we talk about today is, first of all, it's only true for the HotSpot virtual machine. That's what is running in the Oracle JDK and in the Open JDK, right? And I think most of you work with HotSpot, but there are many, many Java virtual machines. There are, for example, the Delvik virtual machine is a very different virtual machine for Java, and it has different performance metrics. So unfortunately, it's very difficult to write a program that's both optimized for Java, or like default Java, and for Android, right? And also these things change. We talk about implementation details today. That's something that isn't specified anywhere. There's no, the Java virtual machine specification doesn't say you have to optimize code in a certain way, right? You can do whatever you want. You can write your own virtual machine and make it do whatever you want as long as it obeys certain rules, but performance is not a criteria here. So please keep that in mind, because if you go on Stack Overflow, for example, and you ask, is reflection slow? That's like one of the typical urban myth that is still around, right? Reflection is not slow. That spoiler to the rest of the session. But it was slow many, many years ago. Java 1.3, Java 1.4, they didn't have the heavy weights that the Java virtual machine has today, right? So please keep that in mind for the future life. Okay, so what we want to look at first is how a Java program is run. And you probably know that already, but just to be all on the same page, let's just quickly walk through it, right? So we all write, for example, Java or any other JVM language. And then we have a compiler, in this case Java C, which translates source code to so-called Java bytecode. And if you came to my session on Monday, you heard a bit about bytecode. And the thing with bytecode is that it is fairly similar to the Java code. The Java C compiler that you all use for compiling your Java program is not an optimizing compiler. It does close to no optimization, right? And the thing is that it doesn't need to. The Java virtual machine is a way more powerful compiler where this bytecode is later either interpreted or at some point it is translated into, from bytecode is interpreted to machine code. And even after the translation to machine code, we still have a step of optimization, because modern processors, they have their own optimizations layers, right? A processor is, for example, reading prefetching memory, right? If you in your Java program read a field, for example, what you do is you read data from somewhere in your memory. The processor might be smart enough to figure out that at some point needs this information and might just load it already in some cache, right? So we have two layers of optimization: the JVM itself, the just-in-time compiler, and the processor, which is doing some optimizations. And developers don't like to look into these layers because it quickly gets a bit complex and complicated, and it's also difficult to obtain this sort of information. It's not really exposed to us. We can look at source code, we can even look at bytecode, but already obtaining machine code from a JVM for the programs that we write is rather difficult compared to other things, right? And today I want to break through this layer with you and look into the JVM layer and the processor layer, right? Also, one thing I should mention is like Scala, for example. If you compile Scala code, the Scala compiler might have to do certain optimizations. They might have to do certain performance optimizations because the JVM, as I mentioned before, isn't this magical box where you can put in anything. The JVM itself recognizes certain patterns and makes use of them, and it's capable of transforming them in a more efficient manner if they resemble the output of the Java compiler, such as what Scala not necessarily resembles to. Tail optimization, tail call optimizations is an example. The JVM doesn't support resolving recursive loops, right? This is a very functional concept, so you have to basically translate this because the JVM doesn't know how to do it, so it's the responsibility of the Scala compiler to do that, right? Okay, so once again, this is HotSpot. How does HotSpot run your code? When you start a program, the JVM has 3 ways of running it. It starts out with an interpreted mode, and then it has 2 different compilers. These compilers were formerly known as the client and the server compiler. And you could actually specify which compiler you would want to use by a parameter, which was -client, -server. Modern JVMs don't do that anymore. Modern JVMs, since Java 8, I think it's default, use so-called tiered compilation. So both compilers are used at the same time. So the JVM, in a way, looks at your code and decides if it wants to step through your program or if it wants to translate your program into machine code, right? And most programs start out to run in interpreted mode. And the thing about HotSpot is it's a method-based compilation. Dalvik, for example, on Android, is not compiling methods as one piece of code. It's compiling loops in a way. So it's not important. I'm not going to talk about Android much, despite I have mentioned it twice already. But as I said before, this is HotSpot. Right? So we start out in interpreted mode. And interpreted mode is so-called level 0. That's if you look at compilation logs and you read level 0, that means interpretation. So the C1 compiler has 3 different modes. It has level 1, 2, and 3. And the HotSpot virtual machine is doing compilation at runtime because it uses profiling. And profiling means that the HotSpot virtual machine looks at your code. It looks how it looks like when it is actually run. And then based on the experience of running your code for a while, it will basically get to know your code in a way, right? How it's actually behaving, and then it will optimize based on that information. And it's a very powerful concept. If you write a program in C, for example, then you compile it statically. You compile it once and only once, and then you have translated it. And this basically doesn't allow certain optimizations. The C compiler, when it translates something, has to be absolutely sure that this one rule that it applies, this one optimization, doesn't ruin your program in a way. The HotSpot virtual machine is able to wait until runtime and look what's actually happening and then judge based on that information. And as a matter of fact, C1 is collecting this information. And it then later gives it to level 4, the C2 compiler, which uses the created profiles to do optimizations based on that. So what this implies is that C1 on level 2 and 3 collects information that might make your code slower than when it, for example, runs on level 1. And that's what makes it really difficult to talk about performance when you observe a program, because normally you don't know what mode your code is currently running in, right? So, but how does this look in practice? Let's say you start a program, public static void main, right? And you enter, what will happen? You will often, we will always start out at level 0. Let's say we walked a bit through the call stack of your program already, we arrived at some method. And this method is used a lot. And that's why HotSpot, the virtual machine, is called HotSpot. It determines what are the hot areas in your code. And hot in this case means it's run a lot. And then it will, after a while of interpretation, start to profile this hot code. It will say, okay, this seems important, so I have to make sure this is run fast. And then it will be handed over normally. In the typical case, it will move from level 0 to level 3, where the JVM collect some information about your code, like what kind of classes do objects have. Like if you have a parameter of type object, it will look, okay, what actual arguments are assigned to this parameter, right? And then after a while, based on this information, it will compile it to level 4. And then basically your code is as fast as possible. C2 compilation is, however, an expensive operation. So for a virtual machine, it is always important to make a trade-off between how much time do I spend running code and how much time do I spend optimizing code. Because once the JVM is basically trying to analyze what you're doing, what your program is doing, this is time and energy that it cannot spend on actually executing the instructions of your program, right? And that's why some optimizations aren't performed by the JVM. Every optimization comes with a cost, with an overhead. So you have to make a trade-off, and that's what the just-in-time compilation people at Oracle are basically doing for their living. They consider what is a typical Java program, what does a typical programmer do, and if you do strange things in your code, then someone might have said, okay, we could optimize that, but we won't, because normally that's not happening, right? That's the first rule. Apply common sense. Basically, if you want to write performant programs, write good programs, and yeah, you'll see later what good means in practice. But it's a good first rule. It's basically the best. I mean, it's a lame tip, right? Write good programs, and then they will be fast. But in a way, it's true, right? Since C2 compilation is so expensive, it might, however, happen that if there's a huge queue of optimizations, that the virtual machine decides to only go to level 2. Because level 3, where profiling information is collected, collecting information also causes an overhead, right? So you might just go to a mode where you can collect a minimal amount of information until the C2 compiler has capacities again. And then you move over to level 3 and then to level 4. This might just happen because your processor is busy or your C2 compiler is busy. Or, what also a typical case, let's think of a trivial method, a getter, right? What does a getter do? It reads a field and returns it. This is a no-brainer, right? That's not much to optimize here. What happens here, it goes to level 3, says, okay, this is trivial. I won't even compile this. I won't spend the energy in C2. I'll just drop back to C1. And this is the typical patterns that you see in a compilation log, compiling to level 3, compiling to level 4, or the other ones, right? Okay. So much for the theory. That's basically the general framework of what HotSpot does, right? But let's look at something more practical. And this is the central building block of HotSpot, of the JVM and how it optimizes code. And the concept is called a call site, and you might have heard of call sites, right? So what's a call site? Well, this is a call site. For example, every time in your program where you call a method, in performance speak, this is called a call site, or not only performance speak. The closer you are to the VM, you often refer to this as call sites rather than calling a method, right? It's probably more exact. And what you all know about Java is that all non-private methods and non-static methods are dispatched virtually, right? So when we call bar here on an object foo, we don't know if we actually observe the class foo up there, if we actually observe an instance of foo, or if we observe a subclass, right? And many languages have therefore chosen to make methods non-virtual by default. If you wrote C++ code, or if you wrote, I think C# also has non-virtual methods by default, they decided to not make methods virtual by default. And the reason for that is not that it's a bad feature necessarily. It's always good to have the possibility at least to override methods if you need to, but this is slow. And why is that slow? It's because you have at runtime or at compile time, you have to determine first what method you will call when you reach a call site. Can you just print hello, like in foo bar, or is the method overwritten? So we have an indirection, and indirections are bad because every time we reach a call site, we have to determine what class is responsible for dispatching the method. And it might not sound like much, and it won't be much, but look at a Java program. What is it assembled from? It's basically method calls. In an object-oriented language, that's what a program consists of, right? So if something happens as often as a method call, calling a method better be as fast as possible, right? However, this is actually not such a big problem, especially not in Java, which is single inheritance. And single inheritance actually has implications of how you can implement a runtime for a language. In this case, we have so-called virtual method tables. to dispatch, and all like non-C++, which is multiple inheritance, also has virtual method tables, but they look a bit different. So internally, the JVM keeps track of a table where it basically enlists all methods by an index. In this case, we have, I have to look at my screen, bar at index 8. And what we then have is a machine address where we reference the code to this method. And there we will just point to this println instruction, right? So if we go to a call site and we observe a class foo, which is actually an instance of this class, a direct instance, then the JVM just goes to this class's virtual method table, goes to index 8, and calls the code there. So this is 3 indirections. Checking out what class has an instance as a call site, go to the method table, and go to the address of the method in question, right? 3 indirections. That's a lot for something that happens as often as a method call. A good thing about single inheritance is that if we have a subclass of foo, then we will find the bar reference again at index 8. So at least the JVM can point to a certain index in a table, so we save us some extra trouble. If every method would be dispatched that way, if we would always go to a virtual method table for every method, Java would be a very slow language. And in the earlier days, Java was a rather slow language because the just-in-time compilation, I think they added HotSpot only in version 1.3, right? And it improved a lot ever since. So how can we improve this? And this is not what the JVM does, but this would be a way. We could get rid of one optimization, one indirection by just maintaining a cache of classes, right? You could just say, okay, the class foo has a certain address for this method bar, right? And Smalltalk, for example, was implemented that way. Smalltalk kept inline caches at every call site. The problem is that these caches are pretty big, first of all, in a way, and consume a lot of memory. The second problem is that we still have 2 indirections. So this is not something that is very feasible for HotSpot. Because this is we still have to check the instance of a class and then check the cache for this instance. And if we don't miss the cache, right, then we have to do virtual method lookup. But in case that we always hit the cache, then we can just walk directly to the method implementation. So what we rather want to have, and this is something that is very crucial to performant Java programs, is a call site that is, one says, monomorphic or linked. A monomorphic call site means that there's only one possible class that is ever observed at a certain call site. So all instances for val will always be of class foo, right? Only foo and nothing else ever. And what the JVM then does is it says, okay, we just go to the call site, to this system out println directly, right? We have basically what the JVM does, it adds a guarding instruction that makes sure, okay, this is really foo, and then we jump to the system out println thing. And this is something a C program cannot do. The JVM makes speculative optimizations. The JVM looks into your program and just says, okay, let's just pretend we don't have a virtual method here. Let's just pretend that we can dispatch this as it was a static method call. This will never be overridden. And only if this assumption is never true, then we have to have like an assert, and then we fall out and do something else. The JVM can do that, basically say, okay, what I tried to do didn't work out, but if this works out most of the time, and it does work out most of the time, then I win a lot of time for not having to dispatch methods virtually, right? So, and this is also profile-based information, right? When we run in C1, we can collect information about what object we actually observe within this foo method here, or the do something method here, I mean. And we can see, okay, is this really always the same class that we observe here, or do we have a lot of polymorphism here? And based on that information from the profile, we can run C2 compilation where we can then put this assert in. All right, so what is there? The JVM knows monomorphic or so-called link call sites. And as a matter of fact, in a general Java program, about 90% of all call sites are monomorphic. Think about getter methods, for example, or setters, or most methods that you write, right? You have classes that are never subclassed. The JVM will just consider these classes as non-virtual after a while, and it will just apply this monomorphism that we just saw. There won't be a virtual method dispatch. It would be as if we had a C# program or a C++ program where we always correctly said, okay, this method is non-virtual, right? This is the same result in the end. However, for example, specifically for data structures like sets or lists, we sometimes have bimorphic call sites. And bimorphic call sites means that we have a call, like let's say we call size on a list object, and then sometimes it's an array list and sometimes it's a linked list. And then we have a similar optimization. And what we don't want to have is so-called megamorphic call sites. And this is basically the first way of avoiding slow programs is to avoid megamorphic call sites where the JVM actually has to do the virtual method table lookup that I showed you before. But since the JVM is an adaptive model, a call site might be in different states throughout the life of the application. So what will happen is that once we start out a program, we probably have to look up the target of a method. And then when we, or the JVM, not we, the JVM gets confident enough that the method is actually monomorphic, we just collapse the call site into being a directly inlined method call. However, if this assumption doesn't hold anymore, we just fall back, we de-optimize the program to do a virtual method lookup again. This is constantly happening. Your Java program is constantly moving. It might be that you have a long-running application that has been online for a month, and then you change a configuration property where different code gets triggered, right? And then the JVM will learn, okay, something has changed. All of my assertions that I put into the application suddenly fail all of the time. And then it will de-optimize your program, but after a while it will optimize it again. And most of the time it's okay, but for some people it's not. If you're, for example, a trading system and you have to be really fast because otherwise you're losing a lot of money, then you don't want to have a de-optimization happening while you're in the heat of the market, right? So some people have adapted, they fire fake data at the application at certain times just to trigger a certain de-optimization and re-optimization of the JVM, right? But again, this is why when you write your own benchmarks, for example, and you look at how code behaves, you never know what's happening, right, in your benchmark. Maybe the JVM is learning about your program while you're running a benchmark and might start optimizing, which takes a lot of time. And you think that something is slow, that it's actually very fast. So this is something that is important to know about JVM. Or not only about HotSpot, actually, this is basically any Java virtual machine that uses just a time compilation. Okay. We've seen this before. Why is this? It doesn't sound so important, but monomorphism is referred to as the Uber optimization of the Java virtual machine. And not only monomorphism, it's so-called inlining that is important. The thing is that inlining is almost always only applied for monomorphic call sites. If this assertion holds, we can optimize the program further. We can just copy the system out println into the do something method. And now we can just run this as if we had copied the code there ourselves. So we don't have to do it. We can just write nicely object-oriented programs, and the JVM does the optimization work for us. Since we could prove that we will always end up calling system.out.println hello anyways, why not just copy this information to where we otherwise would have called the method? And this often gives a lot of space for doing other optimizations. Once you have a lot of code in a method, you have a lot of stuff to think about. And as I said, the HotSpot regards a method as the compilation unit. It treats as a main point. If you can copy a lot of code in one method, you can do further optimizations. And that's the easiest to understand, actually. Oh, no, I have something else before. So now we have, this is the first really practical advice. So we have learned that monomorphism is important. And what you should learn from this is that you should not introduce types into your program when these types are not really used for modeling actual complexity or actual behavior. Let's say you have a list call site and you call list size, right, on this call site here, size being the call site. And let's say normally you either have an array list or a linked list. Then this is bimorphic, right? Bimorphism still means that the JVM does a lot of optimizations compared to a megamorphic call site. But now, not you, of course, but a colleague of yours puts in this array list here. And this is a fancy style of initializing a list, right? And you shouldn't use it because it creates an anonymous class which carries a reference to its outer class, which might cause a memory leak. But in this case, the worst part is that if the list size call site now observes this array list subclass here, we have a third type. And the JVM will fall out from bimorphism to megamorphism. And that forbids more way to trigger certain optimizations that we have seen before, right? So this isn't a real type, right? But the JVM will regard it as a type because it said, okay, normally people don't do these things, so we don't have to take into consideration that people just create a lot of anonymous types without using them. Also, if you refactor a program to represent the same things as fewer types, but in a better delegation model, for example, this might cause your program to trigger certain optimizations, because fewer types means more inlining, more monomorphism, right? So avoid types at all costs, actually, and that might sound strange, but if the problem with polymorphism is that if you actually use it, it might forbid certain optimization. And if it's necessary, then there's complexity that you have to model, right? So then it's okay. But if this complexity is only there because you haven't written like clean and clear code, then you pay for it by performance losses, right? So let's look at another practical example. Let's look at this. Yeah. Yes, please. Yeah. No. First of all, we're talking about very small performance gains here, right? You should write a good program. It probably pays off more to write a good program than it pays off to do these sort of micro-optimizations. It's just what I'm trying to teach you here is that this has implications for performance. You should model, if you really need a linked list, the linked list might have so much better performance implications for a certain use case that this pays off, right? And compared to losing the monomorphism. And actually another thing, it's just stay with me for this example, and then I'll refer back to what you just said, right? Let's look at this log method, right? This log method is very generic, and log methods are normally very generic because they run random arguments, right? And if with the knowledge that we just gained, this is a terrible method, right? We have an array of arguments, and then we iterate over them and call toString on every argument. And probably we will observe a lot of different types here, right? Within this loop, by design already. And toString here will be super megamorphic, right? This will be a blocker in our application. So let's say we call log from somewhere, right? The log method call here itself, it's a static method call. Static call is always monomorphic. A static method call will always arrive at some target. It's never virtual, right? And we just learned that for non-virtual methods, we can inline code. So what happens is that this will be inlined, probably, right? What we now also have is that we know the arguments in advance. We know the 3 arguments that will always ever appear at toString here. What the JVM does for small loops is so-called loop unrolling. So it will replace the loop with a copy of the method body, like this. And what we have created now is that we have reduced this megamorphic call site into 3 monomorphic call sites. So the JVM will be able to do further optimizations by basically specializing each system out println for a certain type, right? And that's very handy because, of course, we could otherwise argue if we have very critical code, like an algorithm that runs for hours, then this is something we should otherwise do ourselves. But since we wrote our code in a way that the JVM is able to perform these optimizations, we're lucky, and this gets there for free after a while. Think, however, about what would happen if the log method would not have been monomorphic, if you had some weird logging logic where the actual logging code is very nested somewhere, and the JVM cannot figure out how to copy this code into your actual do something method. This optimization won't happen. And that's why monomorphism is so important. If you have a monomorphic list, there's very little code entailed, right? But if you have a monomorphic algorithm that is like a huge piece of runtime code, then not being able to do optimizations by merging this algorithm with the actual data might have a very severe impact. However, if it's a very small, if it's a very small segment of code that is behind your inlining, then it's not that bad most of the times, right? And also, what will happen, maybe if you use a linked list instead of an array list, maybe in these cases, you call your algorithm from a different method, right? And then this might be copied into the algorithm and basically create a new call site only for the linked list, right? So in a way, if you structure your code properly, then most of the time, everything goes well. All right. So I have these performance rules, and I try to ridicule it a bit, because these advices, like, right, you would go out now and say, like, this guy told me to never use linked lists. That's not what I'm trying to tell you. Take these performance advices very relatively. You write good code, and only if you ever have a problem, you think about the performance implications. Or if you have to argue with a colleague while certain things should be done in a certain manner, then it's good to know about these things. But never actively think about performance while writing code. So of course, one type is good and many types is bad, right? This is true in a way, right? But it doesn't mean that you should put all your code into static methods and not write object-oriented programs, right? That's important. Okay, and this is something I'm a strong advocate for static typing. I've always been one. I never was a big fan of writing huge business applications in dynamic languages, and here's why. It's a lot about performance again. And what I'm quickly want to do, I know this is Java 1 and we talk about Java, I want to look at a JavaScript program and V8, the engine that's running Chrome and that's running Node.js, right? So how does Node.js optimize code? Can it use the approach that we just explained? Can it use monomorphism and then these concepts? It cannot, because there aren't types. But that's the only way to optimize programs. So what V8 actually does is that it introduces types to your JavaScript code. So let's say you have this object, foo, which doesn't have a type, and you add two properties to it. Node.js will then create a type. The star is basically the type of the empty object. And Node.js, or V8 rather, knows an inheritance model. If you define x first, it will define a type x that inherits from star. And then with y, it will introduce a type xy that inherits from x and star. And this is, in a way, a subclassing hierarchy. So if you have bar, another object which is exactly identical, it has two properties, y and x, but this time we define them in a different order. We will get a different type. We will get a type star again for the empty object, but now we will get y inheriting from star and yx inheriting from y. And the V8 won't be able to basically connect these two types together and do basically a monomorphism optimization for observing these two different objects. And in a way, computers are strictly typed, right? You shift bits and bytes on the hardware, and then people like to refer to this as mechanical sympathy, right? You should think you write software that's run by computers. Computers can just do so much. And if you write a JavaScript program, the only way that the JavaScript program will be performant is by basically being very strict about the shapes of your objects, which are in a form types, right? So even if you don't write typed programs, you will have to have structure in these programs, right? If a program doesn't have structure, it's difficult to optimize. And that's true that's why I'm telling the story, right? Structure, predictability is good. Computers can work with that, and JVMs as well, right? So you want to avoid a mess, and explicit typing is a good way of doing that. All right, so what we could do now, and this is basically just another side of the same coin, we could argue that if polymorphism is bad, we just do branching. And branching is a word for if-else, right? So we can just say if that is true, instance of, call, instance of, and we have created two call sites, right? However, branching is another form of unpredictability, and the JVM has also measures to improve that, and also the processes especially. So let's just quickly look at this program. What we're doing here is we create an array with 20,000 elements and with a random value between 0 and 99. Yeah? Okay, this is what this program does. And then we 1,000 times iterate over all these values and calculate the sum of it, but not the actual sum, but we will add the number if the number is bigger than 50, and we will subtract it if it's lower than 50. And you might wonder, how can you optimize this program? And there's a surprising answer to that. So yeah, because one problem that we have here is that this is inconditional. The JVM is basically forced to do a different thing based on a random value. And since the values are truly random here, chances are 50-50 to either do a plus, like add something, or subtract something. And simply the same thing as with polymorphism, if the JVM doesn't know what's happening, it cannot do certain optimizations, and that's a problem here. So in order to, and the processor cannot predict stuff either. So in order to improve the performance of this program, we can sort the array. And despite us doing additional work, this program will run faster. And the idea is that if we know that the array is sorted, we will probably just jump to the sum, like to adding a number for the first 500 values on average, and then we will jump to subtracting a number for the next 500 values. And since we basically, JVM will be able then to figure out, okay, we do now for 500 values, we add the numbers, so we can just basically start adding without the conditional, right? And then it will at some point say, okay, this is not longer true, this condition bigger than 50 is not longer true, I have to fall back to subtracting, and then we can also fast track this operation, right? So as with polymorphism, for branching, so if else, it's just the same thing. Be predictive. If you can reduce the complexity of your domain to an extent that the JVM can figure out for most of the time how branching works, you will be able to gain a lot of performance here, right? Okay, so in a way, prediction is good. If the JVM can figure out what you're going to do, it has a lot of stuff to look forward to, and it can say, okay, this is going to happen, so I'm going to crunch all this to a smaller operation, which is resulting in the same thing. If the JVM cannot say more than 10 steps ahead what's happening, there's very little to go through, right? The JVM will not be able to tell what's going to happen in the next future, and it doesn't have any information about your program that it can optimize. And that's very important, that's very crucial. If you actually, like if you have an algorithm, right? And your algorithm is alternating all of the time between two different states, the JVM will have a problem. Rather do one thing first and do it all the time, and then change to doing something else. That's, of course, again, a very abstract way of giving performance advice, but that's why people perceive performance as difficult. But this is basically the moral you can learn from this. Okay, let's look into a different optimization that the Java virtual machine does for you. You probably have heard already, this has been true for a long, long time, that object pooling is not a good idea. Object pooling means you keep objects around for as long as you can. And the thing about objects is that they are expensive. Objects have to be allocated on the so-called heap of the Java virtual machine's memory, and that is basically in a away space. It requires synchronization to a certain extent because multiple threads can access the heap, so you should be careful with whenever you create an object. If you look at this example, you will see that there's an object created because this is more or less synthetic sugar for this instruction, right? We create an iterator and then we iterate as long as there's new elements and print out every element from the list, right? And we allocate an iterator, and we want to avoid that ideally. So how can we do that? We could, of course, do the old form of iteration. We could just iterate over an index and avoid the allocation. However, escape analysis helps us to avoid this. If the JVM can determine that an object will not live very long, it can often say, okay, then I won't allocate it in the first place. And opposite to what was done in the old days of Java, where you would keep objects around for as long as you could in order to avoid an allocation, today you can try to keep them around as little as you can and have an even better benefit by not allocating the object at all. The JVM will in a way erase the iterator and just implement the same logic that it represents directly in the method. So it will rewrite your code to not have this iterator allocated at all. So you shouldn't worry about these small iterations. Keep scope small, and the JVM will honor that by deleting objects that you don't actually treat as an object. At some point, we will get value types in Java, and then hopefully this heap allocation problem is reduced heavily again, but it already today is reduced to a certain extent by escape analysis. All right? Okay. So the stack is good, object allocation is bad. That's a general advice. Again, don't take it too seriously. Don't write programs that never allocate objects. In the end, the JVM hopefully can optimize your code anyways. Okay. Let's look at another concept. Let's look at dead code elimination. Dead code elimination is often a very big catch in benchmarks. And what we do here is we have written a benchmark. We want to measure how long it takes to add 20,000 random values. So what do you think will happen here? Well, the JVM will look at this code here and say like, okay, wow, we're iterating 20,000 times over an object and we're computing a sum. But then it says, okay, but we're never going to use this sum, so I cannot execute this. I can just throw this away. So what your benchmark is doing now, it basically measures how long it takes to call current time millis 2 times. And there's another mistake in this program, so this code will also be deleted. So there's another problem in this code, and that is that current time milliseconds is synchronized with the time of your system. But it is not constantly synchronized, it is only synchronized that and that many clock cycles. So what can happen is that you call current time millis for the first time, and then the operating system tells the JVM, you're out of sync with your time, and it will reset the time to a smaller value, and this system out println will actually print out took -1 milliseconds, right? Or even bigger numbers. So in most cases, we'll just print 0 milliseconds because there's a certain granularity. So you shouldn't use current milliseconds anyways, but the main part is that your code isn't actually run. And that's all, again, a very powerful optimization. Let's say we have a method that doesn't do anything. And what the JVM will do at some point, it will just say, okay, I'm never going to call this method again, right? I'm just going to remove this piece of the code. There is, however, a better way to writing benchmarks. You shouldn't write your own benchmarks, but let's look at this example where we fix this. And if you have looked at benchmark code, this is what you will see, right? You have, in this example, what we first do is we do a so-called warm-up. And I've shown you profile-based optimization before. What we basically do is that we ensure that the JVM has learned as much as possible about a program. So we iterate about our actual benchmark code, which is now contained in its own method. And by doing that, we give the JVM an opportunity to learn as much as it can. Then also we use nanotime. Nanotime doesn't have a big advantage, but in a real application, but nanotime isn't synchronized with the operating system. So if you compute differences of time, nanotime is always better. And then also what we do is that we print out the result of our computation, because that way we basically force the JVM to actually compute the sum. Without doing that, the JVM could just, again, discard our code completely, but it can't say, okay, you're not actually reading the console, right? This is a benchmark, so you don't ever look at your console, I won't print it. That's nothing that the JVM can legally do. And then we print the time. So what we basically do is we have a warm-up, and then after 10,000 times, we can be rather certain for HotSpot that all optimizations were triggered, and then we can actually print the results. So this time we have written a benchmark that we can actually use, and this is how people write benchmarks, more or less. Most benchmarks look like something like this. There's, however, a better way. There's a framework called JMH, Java Micro Benchmarking Harness. JMH is a part of the OpenJDK, and it is basically a canonical way of implementing benchmarks. So what JMH does all the hard work for you. You basically have a setup method where you initialize your code so that you are ready to run the benchmark. And then you run the benchmark, you implement it just in one method, and JMH will take care for you that no optimizations outside of this method is triggered. So for example, you return the sum, and then JMH figures out for you how this value is escaped in a way such that dead code elimination is not applied. And it's a really, really good framework. I use it for all of my open source projects. If I have crucial code where I care about performance, it is a really easy way compared to what you had to do manually in order to ensure that the way you implement things are the ideal way to solving a problem, right? Okay, so one problem about measuring performance is that if you run a micro benchmark, and people like to do that because they like to prove that one way of doing things is the fastest way. If you run a micro benchmark and you have two operations and you benchmark them both, you cannot tell that both operations chained together will actually take the time of the sum of these two benchmarks together, because if you run code together, the JVM can, for example, in the worst case, you're doing 2 heavy operations twice, right? If you do the second time, the JVM, if you run it in a row, can then tell, okay, this is the same thing, I just reused the results from before. So you cannot really tell from a micro benchmark if something is fast or slow in a certain context. You have to be really careful what you're measuring, right? In the worst case, it can even be slower to run 2 things after another if you have created a certain profile. Because as I said before, you have profile-based optimization, where a profile is built and certain optimizations is triggered. And since de-optimization takes time as well, if you have to de-optimize first before running your second piece of code, this will cost you, right? Okay, so again, harnesses are good, self-made code is bad, right? Simple rules. One last thing that you should know about, in my opinion, every Java developer should know about are intrinsics. If you look into the implementation of Java long integer, there's a method called bit count. And bit count basically counts all the 1 bits of a number. So this is how bit count is implemented in the OpenJDK, right? However, there's an instruction, a machine code instruction called pop count that is available on Intel, I think. So what the JVM does is that it knows certain methods, and these methods are called intrinsic. If you copy this code into your own method, this bit count method, it will be slower than when you call integer bit count, for the simple fact that the JVM knows this method and automatically reduces it to a certain processor instruction, right? So it is important that if you know certain methods, especially in the context of mathematics, the math class in Java is a very important class, because it is often mapped to certain ways of doing things on the processor level, on the hardware level, right? So this is another thing. And you can actually, if you go into HotSpot, the source code of HotSpot, there's a class called vmsymbols.hpp, where all the intrinsics of HotSpot are listed. So if you write algorithms, mathematical algorithms especially, find out what your intrinsics are and apply them, right, as much as you can. Yeah. Okay, something that the JVM doesn't do for you, and I hope it's trivial, but people misunderstand that, unfortunately, regularly. This is a sorting algorithm, right? But it's not a very good one. What this sorting algorithm does is it sorts or shuffles values as long as they're not sorted. Eventually, they will be sorted if the shuffling is truly random, but it will take a while. The JVM doesn't optimize algorithms for you. Algorithms and what you asked before, data structures, are your concern. If you, for example, collect a lot of items in a list and you probably will never iterate over them, for example, to collect debugging information or something, it is often better to use a linked list. Array lists are almost always the right choice, but sometimes linked lists have much better performance implications. It's not often something related to memory layout for linked lists and array lists, but you should choose your data structures correctly. Data structures are algorithms as well. This is something that the JVM cannot do for you, right? And always keep that in mind. You have to still describe your program in the appropriate way, and that includes choosing the right collections, that includes choosing the right algorithms, right? Okay, so think about your programs. Analyze what you have to do, and don't just do random things. This will cost you a lot. Okay. I don't have that much time anymore, so I'll jump just quickly about exceptions. Exceptions are a terrible way to implement control flow. Don't emulate an if-else with an exception that you catch. The JVM regards exceptions as something that are rather rare. And there's a great blog post of Alexei Shipilev, who's a performance engineer at Oracle, where he analyzes or compares control flow by exceptions to actual control flow. So what's here on the y-axis is basically the average performance of an operation, and on the x-axis we have how common it is to throw an exception. And if you just look at, for example, the yellow line, which is just a dynamically created exception, if it only happens 10 to the power of -6 times, it is much faster than the black line, which is basically an explicit control flow with if-else. So if you use exceptions to do really, really rare events, then they are the right tool. But let's say you use an exception to indicate wrong password exception, right? So from this class, you can tell that the black line and the yellow line hits at 10 to the power of -3. So if your users, if 100 logins, you have only one wrong login, then already the exception is then slower than an explicit control flow. So really, exceptions are meant for rare cases. Okay, so exceptional control flow is a really bad idea, not only for aesthetic reasons and code readability, but also for performance reasons. Okay. Another thing we want to look into quickly, and then I'm almost through, is false sharing. False sharing is, again, something related to mechanical sympathy. Let's say you have an object that is shared. It's class shared here and has two fields, x and y. And you have two threads where one only works with x and the other one only works with y. And false sharing means that basically these two threads interfere with each other despite them not having a common value, right? That's why it's called false sharing. The thing is that on hardware, you don't read fields. You never read fields on hardware level, you read cache lines. And cache lines might have more than one value. They will always probably, most of the time, they will carry much more than one value. This simple example, we just have 5, 6 values in there, and let's say the other ones belong to other objects, but the 14 and the 7 should be x and y in this case, right? So if we have two processors, and one writes only to x and one only writes to y, then both processors will write to the same cache line, because they will both get this one cache line that contains both values. And one says, okay, this 14 becomes 24, and the second one says the 7 becomes 1. Then we have a contention. These two processes have to figure out how they change their cache lines and have to synchronize their information, despite that these two values don't have anything to do with each other. And this seems very artificial, but it's actually something that I see all of the time. What people like to do sometimes is that they write algorithms that use different threads. Then every thread, for example, has a value in an array. And arrays are always aligned in one row. So they most likely share a cache line. So if you have caches that write to different indices of the same array, this will often cause a lot of performance overhead. What you can do, however, is there's an annotation which is unfortunately internal. So with Java 9, it's not available anymore. But in Java 8, it's called contended, where you force the JVM to put every value on it that is annotated on its own cache line. The old way of doing that is, and you see that in a lot of like high-performance libraries, you see that people add a lot of fields above the x and below the x. And that way you basically create a buffer where the cache line will be taken. But then you have that's not communicating your intent, and you cannot be sure if that is then causing a value to end up on a single cache line for all fields, right? So that's a bad way. The contended annotation is much better, but don't be confused. If you look like an LMAX disruptor or something like that, you will see it there, right? Okay, and this is important, really important. If you look at how much it takes to read something from a cache line or to synchronize something again with main memory, which contention always causes in the end, then that's the times, right? If you need to read something from disk, like if you don't write cache-efficient code, where you basically have to exchange values with the main memory all of the time, or at worst case with the file system, let's say you have a swapping space, right? So you write memory to disk and read that memory again back from disk, where a process instruction can cost 1 nanosecond, and reading from disk 1 megabyte can cost the time that it takes to execute 20 million instructions. And this also is really an important getaway. I've rewritten algorithms for customers. Before, these algorithms were running for 10 to 12 hours. And then just by writing them cache efficiently, basically changing just a few bits, these 8 hours can be reduced sometimes to 1 minute. And it's not because the old algorithm was slow. The thing is, people like to think processors are super fast today. What people don't like to speak about is that these times, what it takes to get something from main memory to a cache, these times have improved by about 10% over the last 10 years, while processor speed has improved magnitudes, right? But if your processor never does anything because the caches aren't filled, then your programs will be slow, and that won't improve anytime soon. The reason that we have more and more cache layers is exactly that. It is because processors get faster, but the time it takes to transport information to a processor didn't improve much. So that's important. Pardon, what did you say? Yeah, you're wasting time, space, right? That's the problem with contention. Otherwise, you could just say, okay, we put everything on a single cache line, right? I just take it that people are leaving for Elton John and not because that's boring. All right. Okay, we're almost through. I'll release you in 5 minutes. You know what that is, right? Well, now you don't, because I didn't before I Googled the relation either. That's Heisenberg's uncertainty principle. And what Heisenberg says is if you observe, I think, an electron, I'm not sure anymore, then once you can observe it, you can either tell how fast it is or where it is. And the same goes a bit for performance measuring. If you want to measure a program, then you often have to change the program in order to make it measurable. But by changing the program, you change the program that you were observing, so you're not observing the same program anymore. So don't be fooled by profilers, and they almost all lie to you. Profilers don't tell you the truth. So don't rely on heap dumps, even on, heap dumps maybe, but almost all information. Like, we all love to look at big graphs, but it's difficult to take data out, and often this data isn't even correct, right? So one example is that we instrument code in order to make it observable. However, I told you before that we optimize, the JVM optimizes code for us, and that might trigger the JVM to be in an inconsistent state sometimes. For example, a constructor is called after an object is allocated. So we have a short amount of time where the object is allocated and exists, but the constructor wasn't yet called. So if we instrument code, we might look this object up, but then it wouldn't be consistent. So we're never allowed to observe the object in its inconsistent state. And for that reason, the JVM has so-called save points. And save points are points where it is where it is safe, of course, to observe a Java program from the outside. And this is how instrumentation works in a way. And a typical approach for profilers is using JVM-TI, the native interface, where you can then basically extract some information about a program. But let's say we have a program that is either in state A or in state B, and we try to observe it. And if we have a sampling profiler, which then basically all 5 seconds tries to check into the program what's happening, it will probably observe this sort of thing. Sometimes it's in state A, and sometimes it's in state B, right? However, if it is never safe to observe this program in state B, the JVM will simply never allow the profiler to take control when the program's in state A, right? So we will always only observe state A instead of state B. Does that mean that program is never in state B? Yeah, so I have to check, I can't really read from here. Does it mean that the program never is in state B? Of course not, but our profiler was never allowed to check. So that's why all the typical profilers lie to you, right? So better options, in my opinion, is the honest profiler. If you are really into performance, you should look at that program at some point in life, which doesn't use JVM-TI, but basically Unix interrupts. So it comes from the outside, it says to the JVM, no, now I want to have a look, no matter what. And since it's basically not changing the heap, it's okay to do that. But the JVM wouldn't know for general application that it is allowed to go into the program. Another great profile is mission control from Oracle, which basically reuses information that is available anyways by garbage collectors, by just-in-time compilers. So it has an unfair advantage over other profilers, right?
Quick comment on that before you move on. For flag recorder, I think you may need to set a flag above non-safe points.
Yeah.
Otherwise, you get exactly that.
Yeah, not true for all profiling information. Mission control does both.
Right, so you have to tell it. You may have to look that up.
Yeah, it's true. Yeah, I mean, of course, always walk through even these tools have the limitations, and it would.
It works fine with that setting.
Yeah. Yeah, no, you're absolutely right. I should mention that. The thing is, again, it can do that because the OpenJDK knows in a way that mission control won't ruin anything, right? So that's an important condition. But if you write a generic agent, HotSpot wouldn't know that the agent doesn't access fields and objects, right? Okay, So what you can also do, there's a great tool called JitWatch. It's a part of Adopt OpenJDK, which actually allows you to extract the machine code of a method, right? And that's not always helpful, but it's very interesting to see how some code is optimized and not optimized. If you have very crucial applications, that can give you really good insights. All right. Generally speaking, what I want you to take away today is that you should write good programs. You shouldn't care about performance too much, but it helps if you think about it, right? Okay, so with these words, thank you. That's me. You can find me on Twitter. You can find my open source project ByteBuddy, which was created using a lot of performance analysis. And Documents4J is another open source project that I wrote. Thank you for staying with me. Enjoy Elton John. See you tomorrow, maybe. I give another talk on the memory model tomorrow at 4 if you want to. Otherwise, I'll be around. I won't go to Elton John.